audience present today. I am Alman Mittal from CSE second year.
And I am Fareem Begum from CSE second year.
I am Saimani from CSE second year.
So we would be your hosts for today. Ministry of Education, MOE, Government of India is making every possible effort to drive innovation and entrepreneurship to emerge as one of the focal points of our education system. Thus, MOE has established Institutions Innovation Council, IIC, to systematically foster the culture of innovation. So taking part in this initiative, Institutions Innovation Council of Bengal Institute of Technology, that is IIC BIT 4.0, has successfully completed its 4 years. The primary mandate of IIC BIT has always been to encourage, inspire and nurture its students by providing them support to work with new ideas and to transform their prototypes into success stories. So today marks the beginning of IIC BIT 5.0 and we are back again with our very first seminar on the topic Knowing Present Semiconductor Industry as Motivation for Entrepreneurship. Thereby I would like to take this opportunity to welcome you all to this wonderful session, where I proudly announce that our today's speaker is Mr. Shakti Sivashish Laha. Sir is here today to share his insights and story about entrepreneurship and inspire us so that we could also be among the successful entrepreneurs in the coming future. Now I would like to hand over to my co-host Fareem Begum to continue further.
Thank you, Alman. Now I would like to call our IIT President, IIT Vice President and convener of IIT BIT and our esteemed guest speaker to come up and be seated on the dais. Start with our convener of IIT BIT, Dr. Tapan Kumar Pal, sir. Next, our President of IIT BIT, Dr. Urpila Chakraborty, ma'am. Next, we'll felicitate our guest speaker, Shivashish Laha, sir. Next, we'll felicitate our convener of IIT BIT, Devolina Naik, ma'am.
Now I would request the President of IIC BIT, Dr. Urpila Chakraborty, ma'am, to say something.
To everyone present over here, it gives me immense pleasure to start the first event of IIC 5.0 edition. Like previous years, IIC 4.0, the way you participated, I guess past years are mostly past years a year. But you will be participating this year, you will be getting the opportunity to take part in the events. Today, we are having this seminar on this emerging topic on semiconductor, and we are lucky to have our own alumni student, Mr. Shivashish Laha with us. We will get to know many things about it. And let me ask you one question. How many of you don't have a smartphone? All of you are having. Anyone who doesn't have? No one is there. So what does it do apart from making phone calls? What does it do apart from making phone calls, please? Answer, yeah. What does it do? Now, apart from making phone calls, what do you do with your smartphone? Searching more information. Good means surfing internet, right? Then other than that, what else? Do you watch time from there? Do you use it as torch when the power is off? And what not else? Huh? So how many devices are actually being replaced by this smartphone? This small electronic gadget, how many devices it has been replaced? Just imagine in your own hand the small electronic gadget, and in the other hand the devices which have been replaced by this smart device. So if you just compare and see so many devices. So where these devices or how these devices have gone into this small device? Is it a magic? Yes, students, please answer. Is it a magic? So many devices have entered into this small gadget. What should you say? I should say yes, it's magic. It's magic of technology. It's the applications of semiconductor, right? So with the advancement and enhancement of this industry, semiconductor industry, so many things have been miniaturized, and that's why the things are embedded inside this small device. Now we are not carrying these devices individually. Rather, we just carry this thing. So I think the students who were confused that why are we here to attend this seminar, you got some clue about the program. And when you learn from Mr. Shivashish, today's speaker, you'll get to know the things in details. So with that note, I'll hope for the best for today's. Hope it will be a very successful program and you'll come to know many things. Okay, thank you.
Thank you, ma'am, for your kind words.
Next, I would like to call upon stage our Vice President, Professor Dr. Tapan Kumar Pal, sir, to share a few words.
All of you. This is the beginning of IIC BIT 5.0. This is the first seminar in this IIC 5.0 event. This is the opportunity for you to know different kind of scope of different area, either technological area or innovative area or other things, to basically identify different type of area and what kind of solution you can have. And this is basically the one platform that is very important is entrepreneurship. And you know that entrepreneurship is nowadays in all over the world. It is one kind of boom. And Government of India is also initiative to initiate this entrepreneurship program among all the technological students. This is because the scope of job for multinational companies is not bigger, not flourished today. So that's why entrepreneurship, if you adopt this kind of entrepreneurship program, so you have a freedom for your lifestyle, or you have some freedom for doing their work Because today work is working place, I think, is very problematic. Suppose in technology sections there are a few, not only 8 hours, there are long 10 hours, 12 hours durations is there. So that's why there is some trace, there is different kind of trace is generated. And to minimize this trace, so if you think about entrepreneurship, so you have own business. If you have this own business, you get opportunity to others to to create some job, as also you have some freedom to earn some things. You have a joy for doing new things. So this is that's why the IIC BIT or initiative this kind of seminars, so that you should know about different area that can have very important scope for creating this entrepreneurship. One of it is semiconductor. I think you know that semiconductor is basically a small device, but it has huge application in any kind of electronic gadgets, computer, smartphone, etc., etc. And you know that the total business turnover of all of the world in semiconductor is increasing rapidly. In 2018, the total market is about $450 billion. In 2021, it increases 555, and it's expected that in 2027 it should be go $750 billion. So that's why it is very important this time to make some entrepreneurship program about this semiconductor. So that's why today the speaker, the Shivaji Laha, this is our own alumni, and they gives about the semiconductor, what is the applications and what are the different type of scopes that creates entrepreneurship journey among this semiconductor. Okay, so let's go to the seminar, main seminar for the topic. Thank you.
Thank you, sir, for your kind words. Now I would like to call the convener of ICBIT, Professor Devina Gauri ma'am, to share something.
Good afternoon to all and everyone present here. I would like to greet and I want to heartily welcome the new first year students of BIT. All the students means I want to just share a few words about IIC. What IIC is all about, as you know, it's an MOE's Ministry of Education has been incorporating IIC in different colleges, and IIC as a part of IIC we are performing different events, programs, different innovative ideas are coming, entrepreneurship cells are being developing, incubation cells. These are all types of cells that are being developed from IIC, and you can showcase your ideas, your innovations in different. You must have gone through the WhatsApp groups, poster making group, and also the another group you have joined. Anchoring group, so you can showcase your ideas not only in this innovative ideas, not only in these two groups, but also you can showcase your new innovations, new ideas, and there is a UP portal where we can upload new ideas, and there are huge means cash prizes as well as huge prizes they are giving from MOE. So this different portals there are where you can showcase your innovation, your ideas, your new projects. I hope all the first year students will be involved means thoroughly and means sincerely from the first year itself and come up with new ideas and help IIC to grow further. With these words, I would like to thank all the students, all the faculties present here, and most importantly, our guest speaker, Shivaji Laha, present here for giving his valuable time with his tough schedule. Also, he has come to share his thoughts to us. Thank you.
Thank you, ma'am, for your kind words. Now I would like to request our guest speakers and faculty members to get back to their respective seats. Now I would like to request my co-host Saya Mehdi to introduce our guest speaker.
Well, it gives me immense pleasure to say that our guest speaker, Mr. Shivashis, is our own alumni. He has been a technology enthusiast in automotive electronics. Currently, he is working as a project quality engineer at Nexperia R&D Fab Lab in Hamburg, Germany. Besides getting a BTech degree in Electronics and Communication Engineering, he is pursuing Master of Science in Microelectronics and Microsystems as working student from Hamburg University of Technology. Now, I would request our guest speaker to please take over. Over to you, sir.
Hello. Am I audible at the back? Hi, everyone. Thanks to my dear teachers, thank both of them and everybody who is in front of me and participated in this seminar. So I just don't want to say it as a seminar, but rather a discussion. I think most of you know about semiconductors, have heard about this term. So we'll have a short amount of discussion. I have prepared some material. Features, please.
So many electronic gadgets.
Yeah. So we can see some monitors, pen drives, or some consoles, some gaming consoles, etc., etc. Correct. So, but let's see inside. What is it? Now, do you know all these things? So when we open up these things, the gadgets, you will be able to see some components like this, this, and this. Right? Are you familiar with these things or not? Yeah. Okay, that's cool. All right. And when you deep dive a little bit, you'll see that some LED strips are there, like in gaming PCs. Some of you have gaming rigs or gaming PCs at house? No? Okay. Yeah.
Okay, and this you might not be familiar, but we all have in our smartphone. This is the Qualcomm Snapdragon processor or the system on chip. These are again all the semiconductor chips and different kinds of diodes and discrete devices. So let's see some more devices when we expand. So you can see this is a module for a camera. So you have a smartphone camera and everybody loves selfies, right? The hardware behind the selfies is this tiny camera. This one is called an accelerometer. So, for example, when you drive a car and then you push a brake just in a moment, then the airbag comes out. So this is being sensed by the accelerometer. Then you have some other sensors like gyro. Then a pressure sensor that can sense pressure for water, fluids, and different fluids. Then these are some of the 5G chips that you are most familiar. Like I think in end of 2023, 5G will be rolling out in India, right? Or start of 2023. Yeah. So this is the chip which is responsible for all the only the 5G communication. Then this is the infrared camera that can sense heat signatures or like that. This is again some sensors, and if you see this sensor, like this is an implant that we have made at our university in Hamburg. So this is basically a retinal implant. So for example, for those blind people who has, like for those people who have some issues with their retina and they can't see, so we can use this semiconductor technology. We can fabricate some devices, and we can replace the organic retina with this biocompatible sensor. Then you can see this is a tiny kind of. Yeah.
In medical science, in this time or something we have to see. That's why they put a small pipe there.
Yeah. So, and this process is quite complicated for medical sciences as well, and for the patient as well. It's horrible. So, what we do is like, you can take this and you can just consume this pill, and then it will go inside your intestine and it will take a photograph, and then it will come out from your stool. So, yeah, it was like, it will save a lot of time and a lot of pain for you, and this will scan. So, welcome to the world of nanocosmos. Now, I'll show you something. So, this is basically a microphone. So, this is what I'm talking with, not like this. Maybe you have a smartphone like this, and you have a microphone in the smartphone. And the smartphone is technically it's called a MEMS smartphone or microelectrical mechanical machine. So this looks like from top like this. You can see there's a small hole, and from here, our voice goes in. Now, if I open this, let's just open the cap. Are you able to understand? Yes. Okay, good. So when you open the cap, you'll see that the device looks like this. And this is the diaphragm through which it oscillates or vibrates, and this is the AC or the electronic circuit. Now, if I open again, you will see that there were some bonds. You could see some wires there, and now I have just torn out these wires, and you can see that this is the diaphragm and this is the electronics. Now, this was actually designed by Samsung. This is the Samsung's patented MEMS microphone. So you can see the diaphragm over here, and the diaphragm does is when you speak, the diaphragm vibrates and it produces a mechanical wave, which is being transferred to these electronic devices, and then these mechanical vibrations are transformed to electrical impulses, and then with the help of these devices, with the help of these electronics, it is transformed to digital circuit or digital signals, and then we'll require Orbiter and cell to process it with the DSPs. Yeah. All right, let's move on to some other sensors. So this is basically an accelerometer, which I told you beforehand. This accelerometer that works in the way that whenever you are driving a car, so you can see like whenever you just push the brake, like when you are in front of an accident or you have to save someone, you push the brake, then the airbag pops out. And how does it sense this? It uses an accelerometer, so it uses the acceleration of the car, and then when the acceleration is more, like whenever you press the brake, then it senses and then it triggers the ABS or the airbag systems. Also, I think there's an app in Android where you can see the acceleration. Wait, I'll just show you. Do you see, sir? So there are some acceleration sensors, the different kind of sensors. Rotation vector, gravity, light, gyroscope, orientation, acceleration. So we have all these sensors embedded in a smartphone. See, when I'm walking, you see that there's an acceleration. Okay? It's called CQZ. On the top. See, the values are changing. This is the accelerometer that is installed in this smartphone. You all have it in your smartphone. And with this also you play the most interesting game, the car racing ones, right? You tilt the phone like this, that's how it works. Alright. So this is a two-way integration. One is the actuation, where you have to couple the physics, and then the second is the electronics part, where you have to transfer the signal to electrical noise. So this is the mechanical part, which vibrates, and this is the electronics part, which converts the signal to electrical noise. Now, you see that there are some spokes. I think, here you'll be able to see in detail. So there are some, like, what should I say, horns or some spokes. And these are basically capacitors. So I'll show you how it works. Just look at this video very, very carefully. You'll see some oscillations or vibrations. So whenever we walk, this will vibrate. Here you will see some changes. You see, this is rotating, this is moving. Here you will see also these are moving. So these are like two plates of a capacitor. So whenever the plates of a capacitor moves, the capacitance changes, and with this it senses. We can register this change of capacitance. This is called also angular rate sensor. All right. And this is what is called an integrated circuit. Am I correct? Or am I wrong? Okay. Let's see. So this is how an integrated circuit looks like. And when I open it up, you can see there are some wires, and these are called the bonds, or the wire bonds. And this is the silicon crystal, where they are connected. Now, the fun part is, you can see, when I zoom it up in microscope for about 100x, you can see that these are different interconnects and layers of metallization, like the integrated circuit that are present. And you can see also some images that were made by engineers, like playing cards and some of that. Okay. Yeah. So also, an image like this in a very small chip like this. Alright. Yeah. Now I think a little bit of physics. But beforehand, I would like to ask you, like, do you have any questions till now? Like, I have just shown you some devices, like how it looks like from inside. Do you have any questions or if someone doesn't understand? Yeah, we'll see. We'll see in the upcoming slides. Definitely. Thank you for your interest. Yeah, good question, sir. So these are all in the micron machines. So for example, 10 micron or 20 microns. So all the small hoops. They can be also smaller than that. So we etch it, we fabricate it using different chemicals, and there are also physical plasmas as well. Alright. So let's see what are semiconductors and how it is made. I think it will be also important for your first year question papers as well, I guess. So yeah, just make yourself familiar with this. Alright. This is a periodic table. I'm not going to explain it to you. Don't get intimidated. Alright. So okay, we'll see this area. Okay? This is our interest. So you see this silicon, this is one of the semiconductors. Like the guy who was there in the back just said that it's the conductivity between an insulator and a conductor. We'll see. So this is a very special material, silicon. We can also combine semiconductor, like we can also make composite semiconductor using gallium and arsenide. So these are called composite semiconductor, compound semiconductors. We can also make gallium nitride, and these gallium nitrides are used in the making of power electronics, and gallium arsenide is used in the making of displays. This mobile display you see, these are made up of gallium arsenide phosphate. Then we have this new material called silicon carbide. I mean, it's not new, yes, it was. Now we can produce it in the lab, and this material is very robust, and it's a very good semiconductor for power electronics. It can sustain very high voltage. So let's look into the crystal of an atom, the atomic atoms of a crystallization. So this is called the valence shell, the outermost shell of an electron, of an atom. Now you can see this is the valence band, the outermost shell, and if you induce some heat or if you apply some energy from this valence band, the electrons go to conduction band. In case of conductor, these two bands, the valence and the conduction band, are overlapped. So they are basically they are overlapped. So the electrons always pass. So that's why they conduct electricity readily. But in case of insulator, you see that the valence band and the conduction band, the band gap is so high that the electrons cannot jump. But if you can induce a huge magnitude of energy, then it may be possible that the electrons can fly. Yeah. So let's see, whenever we are introducing heat, you can see that the electrons are flying out, and they're moving into higher energy levels or in the conduction band. And whenever we apply a voltage instead of the heat, like what I said, so we can induce this effect. So silicon at room temperature it behaves like a normal conductor, a normal insulator. Now when we induce some electricity or heat, then it behaves like a conductor. You can see this is how a silicon crystal looks like. And there are three different varieties of crystal. I'm not going to detail physics on it, but just as a note, there are three varieties of the silicon crystal. See a simple application, how we can leverage this semiconductor into something useful. Like from our own application, just a DIY project. Okay, so let us suppose that we have a flow of water, and water is flowing, and we know that whenever the water flows, it has some pressure inside the tube, and we want to sense it somehow. So we have an electronic circuit, and then we want to see in computer what's the pressure. So this is our application. So how we can do that? So this is the basic physics. I mean, like whenever there's a beam, whenever you press it, you'll see that there will be a deformation. And whenever you do a simulation in computer, you'll be able to see that the deformation is maximum in the center, and the stress points are the corners. And we can take this effect of physics to use it our own device to sense pressure. So let's see. So there is a special material called a piezoresistive material, and whenever you bend this material, the resistance changes. There's a piezoresistive and a piezoelectric materials as well. Whenever you bend a piezoelectric, it induces current, and whenever you twist or deform a piezoresistive, it changes the resistance. So now, as you can see, if I put the piezo resistive components over here, so when as the space is high over there, so whenever I bend the device, so this will be bent, and I will be able to change the difference of the resistance, right? Is it okay? Or is it too much? Okay, yeah. Alright, so this is like a cantilever structure, you can see, and I have this piezo resistors on top. So whenever I press it, this will also be formed. And do you know this thing? What is this called? Yes? Wheatstone bridge, yes. So whenever you have these two resistance which is changing, then you can see some voltage change, right? Is it? Am I saying right, or I may be wrong as well? Okay. Alright. So when we have a difference in the voltage, we can feed this signal into an operational amplifier. You will learn it in your third year or second year. You just feed the signal, and this can sense. Voltage. This can predict, this can calculate what's the difference in the voltage, and this can sense a Vout. Okay. And with this, we can measure how much pressure we are getting from this change of the voltage. So it's like a calibration we have to do. Do you understand? So from this cantilever mechanism, we are changing the resistance. From the change of resistance, we are feeding it in like a Wheatstone bridge. And whenever we have a change in the resistance, we have a difference in the voltage. Then we are feeding into an operational amplifier. This actually senses. All right. A device that can sense pressure. Yeah. So silicon wafer looks like this, as you can see. It can be bent as well. Now we are making our own pressure sensor. So we need a clean room kind of atmosphere, where it is like this room is 1,000 times cleaner than operation theater. You can see some of the cross-sectional view. And then we do some thermal oxidation. I mean, this is also physics. I'm not going into much details. So you can see we have the silicon wafer on top of it. We have silicon dioxide, and then we'll have a metallization like a piezo resistors, but we are making in a cantilever structure. And then we can do some photolithography, like screen folding, and etching also. So the previous structure was like this. This is the silicon dioxide, and the metal. After etching, this is so basically this is my silicon, and this is my piezo resistive compound. Yeah. So then I'm etching it on the back side, and now I have this pressure sensor. So whenever you will infuse some water or fluid to it, you can sense the pressure difference. So yeah, I haven't shown you the exact details how I can from the cross-sectional point of view how we can do it, because it's a little bit higher than your level right now, because it should be in the solid state electronics in your chapter in your third year. So after you get through it, you'll be able to understand that. But just for a very short introduction, like how we make this, like photolithography, like oxidation, and then we have these devices. So this is how a transistor is made, and I'm not going to the details again. If you have any questions, I can definitely explain it to you. So we have the silicon wafer, then we are doing some oxidation, we are doing some metallization, and then we have this small structure, metal oxide semiconductor. Alright, so you can see this is how a silicon crystal looks like, and this is, we are doing some implantation to close the silicon. And this is the lithography technique what we do. So this is called a photolithography. So photo means light, and lithography is etching away or cutting it down. So you can see that whenever we want to make a device, we use a mask called a reticle, and then we put the light in a prism, and then this is our wafer where we can have multiple copies of the same device. So you see it's like a scaled down structure. So we have a big device, and then we have multiple copies of the same device. We can make it in a silicon wafer. So one wafer can contain 1,000 or even million transistors or SoC, silicon on system on chip. And this was all before I think in 2005. So previously we used to have this light source like a UV ray, which was about 364 nanometers, and then we put it in the prism, and then we put it in the wafer. But as the time progresses, we all have, so what's the latest nanometer of the devices right now? 5 nanometer, right? But our light source is 364 nanometers. How can we scale it down? That's the question. So some of the clever scientists, what they did was they put water in between, and this is called immersion lithography, by which they can half the wavelength of light. They can increase the resolution of up to 45 nanometers, like with multiple advancements and tweaking. So previously we were generating only 364 nanometers, and then after immersion lithography, we could get about 45 nanometers of resolution. Okay, and this was thanks to this Intel Core i3, i5, and i7. These were all the second generation processors. I think back in 2012 when we had this 45 nanometer technology. But as I said, industry never stops, and we are more getting used to smartphones, and we need more computing power. We need transistors of smaller size. So basically, a transistor has a three elements, like a source, drain, and gate, like a bridge structure: source, drain, and in between gate. So the smaller the transistor gets, the smaller the difference between the source and the drain, the faster it switches, the faster it communicates. But making this is a big challenge because it has a lot of challenge in the physics. So light has 364 nanometer wavelength, like UV ray, what we are doing. So we have to go into X-ray, I think, for laser wavelengths. But that also has some problems and challenges in previous times. So then, after like 30 years of research, like the engineers and the scientists have found a new technique, what we call it the extreme UV lithography. And with this extreme UV lithographer, EUV, we can scale down devices up to 3 nanometers. Yeah, so the wavelength of the light gets attenuated to 30 nanometers, 1, 3, and then we use immersion lithography again to halve it down, to cut it down up to 3 nanometers. So this was a big technological breakthrough. So this is how the EUV chamber looks like. It's a very big machine, and this is made by ASML, and this is like a half of the soccer pitch. Like it's huge. And with this technology, we can get the Snapdragon 8 Gen 1 processor as well as the MediaTek Dimensity 9000 series line of processors, which are 6 nanometers and 4 nanometers respectively. So yeah, so how it performs or how it works? It's very simple. It's like we use a laser source, like a carbon dioxide laser, and then we amplify it. And when we amplify it to a very high extent, and then we drop a tin pellet, it's made up of tin, a small drop of tin. We fire the laser on the tin pellet. After that, the tin pellet explodes, and then it emits a light of 13.5 nanometer, and that is called extreme UV ray. I'll show you a video how it occurs, how it happens. Enjoy this. Yeah. So was it good? Yeah. Yeah. So this is how the modern chips are fabricated. Like getting this light is immensely costly, and it's like a ingenuity, and it's like a pure physics how we can get this light out of this UV lithography. Some people also call it, like some physicists also call it, like X-ray lithography. Like people, like a more industrial guy, they also say UV. It looks more fancy, sounds more fancy. All right. So now we have a device. So I've showed you like we have made a pressure sensor in a fast manner, and also some transistor how we can fabricate it. But can we use it? We have the crystal itself. So I just have the crystal. I'm just giving protein answer. Can she use it? What do you think? Yes or no? Why? Just feel free to answer. Anyone? Why we can't use it? We have a crystal. Huh? Okay. We cannot get the light source. Light source? Okay. Someone else? No? Okay. So the thing is that it's like. So I have only the crystal, right? So for example, if I'm making a car, I have only the motor. That's all. But will you be able to drive the car? No. So you need this chassis, you need these other assemblies as well, right? So packaging is also a different kind of. It's very interesting and important part of the semiconductor industry as well. So now let's see how this packaging, how we can package a particular die. So are we familiar with this in video games? Yeah. No try to do yeah. Yeah. This is called this black area. Okay, not this part. Okay, this is black area. So when I was a child, I just opened a calculator once, and I could not understand what are these. Now I can understand. These are what core or chip on board. So what they have is, in the previous times, they have this silicon crystal inside. Since they don't have any package, they just put an epoxy molding compound, like an epoxy kind of thing, just to seal it, so that the crystal does not get damaged with humidity or temperature, something like that. So previously they used to do like this, but it has to be standardized, right? So as the semiconductor industry matures, we need more chips, and the chips has to be in a standard package so that everyone can use it. Because everyone will not be able to afford this structure, right? Okay. So this is how a MOS transistor looks like. So you can see this is the source, this is the drain, and this is the gate. Just like I showed you, like we have 3 different elements. So the shorter the length between the source and the drain, the faster a transistor can walk. Okay? And this is how the package looks like. So this is like a board or a PCB. And then we wire bond it, you can see, and then we encapsulate it. So this is how a package looks like. And this package is being standardized by JEDEC. Just Google it the name whenever you go home, JEDEC. They have this standard, and this is called DIL package, dual inline, that means dual inline package. Previously we have to use the core, but now since the JEDEC has saved us with the new package, so we can use this technique. And this saves a lot of effort and also have higher reliability. There are some other bonding techniques as well. You can see this is a wire bonding technique. This is the crystal, and from where we are having wires with interconnect. And these wires are about 40 micron in size, 40 micron in diameter. These wires. And since if we need a very high current, for example about 10 amps or 20 amps of current, that's what we need in our semiconductors, then we will simply blow up these wires because they cannot sustain very high amount of current. For that we have to have this clip bonding technique, where we will have a clip that will be sandwiched with a crystal die. So this is for all the integrated circuits. This is for the power MOSFETs. But what about our cutting edge semiconductor processors like Snapdragon or Intel ones? So here we use a technique called the flip chip. So you can see that there are a huge number of points like connectors. So for example, in a power semiconductor you have 2, 3 or maximum 4 connectors. In integrated circuits you can have 14 or 28, like 56 connections at max. But in Intel line of processors or microprocessor you have 100 or 500 or even 1000 interconnects, like contact pads. So how you can do it? So what we do is like we induce some pellets, like some metal balls, and then we flip it while soldering. So in this way, you can see that if you are familiar with motherboards in computer, you'll be able to see that they flip the chip. This is the die, and they flip it so that these will be connected with the motherboard, which is a flip chip technique. This is the most advanced bonding technique right now in the market. And there are some also different kinds of integrated circuits and products. This is from my company where I'm working with. And now we'll see a short video about how semiconductors made, what are semiconductors, and what's going on in today's market. Made from sand to silicon. Okay, so the semiconductor, so we are now very close to the end of our seminar. So the semiconductor market is huge. I mean, like, we only know about chips for semiconductors, but semiconductors can be everywhere. In biomedical implants, in analog and digital circuits. So I have asked one of my colleagues that what is a semiconductor? He told me VLSI. VLSI is only this of the puzzle. So we have analog, mixed signal, then we have ESD protection, power. So there are many aspects. Then we have the sensors, where you can play around with the physics, like the MEMS, like photonics, like you can make some photonics devices, and also LEDs, like display panels, different kinds of new technology, or AMOLED displays, the active matrix organic lighting that which we have in all our smartphones. Then we have microfluidics. I think Sushi Sutaman is not there, that's a field of research. Microfluidics is that field where we can make biocompatible like sensors, and we can implant it in our body. Then we have some communications, like 5G, 4G chips, satellite communication, space electronics as well comes under this semiconductor communication and communication industry. And with this, we have then the next year that is called cyber physical system or the embedded system, from where you will be familiar with your IoT, machine learning, AI, human interaction, and other software-related applications. So this is a generic approach how a system is being made from a device level to an application level. Thank you so much. And there are some useful tips as well. If you are interested for semiconductors, you can read some papers from ICT Explore, and then you can learn about some tools like Cadence, LabVIEW, Verilog, Intergraphics, Otium, and also some simulation software that might be helpful for the future if you're interested for this sector. And also some technologies like whatever I just learned about different kinds of technology like CMOS fabrication. So yeah, so with this we come to our gallery part. So this is, you can see, some convertible silicon carbide. These are some biomedical implants in the clean room. So yeah, I started this from BIT with this motivation in 2016. And this, with this dream that I'll be working also in the fabrication plant, I'll be fabricating my own device. And yeah, that's how I think I motivate you guys all that you are like, I was like, I think 10 years ago from where I started, from your side. And slowly or steadily, if you have this motivation, if you have this learning ability, nothing can stop you. So your perseverance matters.
About this question, how is it possible to make are they maintained in the global boundaries? So, unthinkable enormous decision.
So Mobisar's question was like how global foundries can make these devices with enormous precision. So the thing is that it was not done from day one. Like they have to do it very slowly and steadily. It took them years to have this fabrication plant. So they have to make first of all a huge area. Then they have to clean the dust because in the lithography section where different like light, we are playing around with light. It requires extreme sensitivity. Like it requires that no other sources of light, like especially the polychromatic light, should not come and affect the photoresist that we have. So there are different sectors, and they have their own pumps. They have good, like they have very high quality air conditioners. They filter it out all the air. They have different kinds of filters through which they filter out dust. And for the lights, they use yellow light only. So it's also there in my university where I'm also in the clean room. So yellow light is the standard because it does not affect the photoresist. So if you have any other source of light, it will simply like solidify the photoresist. You will not be able to catch the bottom structure. So it's enormous precision. It comes with experience, with years of practice, and they have all made mistakes, different kinds of failures. They're still making failures. Like Global Foundries is one of the players. I think, have you heard about TSMC? Yes. TSMC is another player as well who are making the fabrication. Then we have the Samsung. Samsung is also another player. I hope this answers your question.
Is it can be used to measure the weight? Because it is useful in close level.
The second question was the pressure sensor. Will you be able to measure weight? Yeah, is it possible? Definitely. Like for example, we have you have all these weight machines right in your house, like the portable ones. So they all have this pressure sensor, and through which they use this deflection of the membrane, through which they can calculate how much is the weight. These are all with actuation. Yeah.
We are coming to the end of the sessions. So on the behalf of Institute Innovation Council BIT, I would extend really hearty vote of thanks to the speaker, Mr. Shivashish Laha, R&D Product Quality Engineers at Nexperia Semiconductors. I will also thanks to our principal sir, Professor Dr. N.C. Ghosh and Professor Devashish Pradhan for their constant support for conducting this kind of event. I also thanks to our IIC BIT President, Professor Dr. Gurmita Chakraborty, convener, Professor Debolina Bari, and also different type of coordinators. Those are creating this kind of event or arranging this type of debate regularly. So on this event, I also thanks to Professor Shubham Nandi and Professor Deepti Majumdar. So they are jointly coordinator of cell-level activity for conducting this kind of seminar. I also thanks to all the faculty members and all the coordinators of IICBIT for their constant support and effortless conducting this kind of regular seminar and other workshop. And at the end, I also thanks to our audience, the student of BIT, and the anchor team, Almaz Akhtar, Fahim Pegam, and Shahan Maidi, second year CSE department. Thank you all.